G'day, my name is Gurnett. Thank you for joining us for this Glencore Technology CMP short course. Today, I will be presenting on a whole series of topics. Midway through the presentation, my colleague, Principal Metallurgist Adam Price, will join and go over some of the key operational factors, why they're important, explain what to do with them, and most importantly, size a Jameson cell for you so you can see how easy it actually is. Aside from that, I'll go over a bit of a welcome remark, and a safety overview, a bit more on who Glencore Technology is and how the Jameson Cell came to be, a bit of a summary on where we have our installations in different developing markets, explain how test work is done and how you can incorporate that into your current test work programs. Adam will touch on the operational factors and sizing, and then I will finish up with a few real-world case studies. So with that, let us begin. Now, before we do any presentation, I always like to do a safety share. Here, I've used a ISOMIL example, and what I really want to stress here is normalization of deviance. When you do a job multiple times, certain things become routine, and hence you start acknowledging acceptable safety risks when they're not really there. Prime example here is there are a whole series of working with suspended loads and housekeeping issues. And I would like to just address some of them so you can see how easy some of the stuff can be missed. Here we have an employee operating a crane. He's taking a disc off an ISOMIL shaft. If you look around, you've got tripping and falling hazards throughout. You have discs laying on their sides. You have stuff left on the rails, spacers not being secured on the ground. You have a load being lifted without a tagline. Stuff lying on buns, and no stop blocks from preventing things from rolling. Most importantly, the guy actually working with the suspended load isn't even taking notice of the crane. As you can see, the guys working around them. And lastly, no gloves. So all I really wanted to do was really remind people that normalization of deviance is a thing. Every time you do a job, you should expect to treat it as it's the first time you're doing it, and that way you can ensure you work safely on the job. Now, Glencore Technology and the Jameson Cell history. Glencore Technology is a technology company that's based in Brisbane, Australia. We've been around a fair while, around 40 years, and we're part of the overall Glencore group. We basically provide 5 core technologies: the ISOMIL, which is a ultrafine grinding mill; the ISOSMELT ISOConvert, which is our pyrometallurgical process; the Albion process, which is an atmospheric leach style process; the Jameson Cell, which we're going to go into a little bit more detail today; and the ISOKID, which is our electrowinning process. Pretty much the core theme here is all these technologies have been developed at Glencore operations, and we offer them worldwide. We have a global footprint for these technologies, and we pretty much operate on every continent. And what really separates us from everyone else is these have been developed on our own operations, and we make sure that they work before they actually get rolled out to the market. And to really stress on that global footprint, we've just got a map of the world here. Shaded in green is where we have technology installations. As you can see, pretty large footprint. We have about 150 employees, contractors. We have offices on every continent, and have pretty much a significant worldwide presence. Now, the Jameson Cell. The Jameson Cell is actually technically deemed a mature technology. We have over 440 of these cells sold worldwide, and these installations are over a wide variety of commodities. We have them in base metals, coal, gold, and we even have them in some bespoke applications such as winemaking and wastewater treatment, which just really highlights the flexibility of the downcomer design. A nice part to mention is it is a mature technology. We have over 35 years of continuous design improvements, and this is something I really like to stress because that really reflects the technology of where it is today. This continuous development has been done and has been categorized via various mark versions of the Jameson Cell. We're on our 5th revision, Mark 5. And over these years, we've basically highlighted a whole series of main achievements, and these being stable operation, high capacity, wash water system to deal with entrainment, recycle to improve process stability, different materials, longer component lives, and probably one of the highlights, the easy maintenance that we can do. As a bit of a spoiler, these cells can have their maintenance done on the run. You don't need to shut down a Jameson cell to do basic maintenance. And this is one of the inherent benefits of the technology. Now, it's my pleasure to go over the Jameson Cell overview and where we actually operate. And I think this will give you a really good idea on where we're at, what we're trying to operate in, and get a bit of information on what's out there. Now, 440 Jameson cells have been installed. We've installed these over 35 countries in about 18 different commodity groups. Probably one of our main markets here has been Australia, which logically makes sense. This is where the Jameson cell was developed. And as you can see, we have a presence in North America, South America, and the CIS regions. A majority of these installations are base metal and coal being a big one in Australia, and gold. If we look at it by commodity, most of the applications are really moving in these days are copper, zinc, and gold. We have been doing additional installations and been growing in popularity, specifically in potash applications, moly, nickel, PGMs, graphite. So we have been trying to grow our market and move into this currently evolving industry, which especially as the industry is moving towards battery style metals. The Jameson cells themselves are a very, very flexible cell design. They can be put in any application. And historically, we've been seeing a lot of success in cleaner circuits, particularly as scalpers, due to the ability to produce a high quality concentrate through that froth washing that you see with the wash water and Jameson cell design. We have a large installation base in fine coal beneficiation plants. This has been done during that big uptick in the Australian coal markets, and have a big base in solvent extraction electrical winds circuits, particularly in recovering of organics. But what I really, really want to stress here is that the Jameson cell design is highly flexible, and it can be put anywhere in your circuit. You just need to configure your cell for that duty. And for that, we have applications for roughers, rougher scalpers, scavengers, free floats, cleaners, and can pretty much do your whole circuit, which we identify as the Jameson concentrator. Now, developing markets. This is where it's been getting quite exciting. We've been seeing a significant increase in roughers, particularly rougher scalpers and traditional rougher circuits. We've seen scavenging applications get put in as well in both the rougher and cleaning circuits, which has really pushed us to do the more full circuit approach. We have seen a lot of interest in moly due to the high kinetics that occur within the downcomer. We've seen great success, and I will touch on some information later on. And are really seeing a lot of intake, particularly on those future critical commodities, i.e. the battery metals. As a bit of a summary, I've put all the different cells and number of cells we have in each of the fields, and it really highlights what was discussed in the previous page. Now let's talk about a few examples. Graphite is a big one. Graphite is something there's been a lot of interest in late, and it's mostly due to the ability for high capacity, low height concentrated designs. Here I've got some test work that was done on a J300, which is a pilot style test rig. This graphite concentrator was considering the Jameson Cell technology for a full-scale application. The J300 is a lab-scale pilot, which replicates the performance of the downcomer in a laboratory. Using the rough rule of thumb that one Jameson cell can replace 3 stages of cleaning, we found that utilizing 3 stages of Jameson cells was equivalent to 9 stages of mechanical cleaning. When we put this all together, we developed this grade recovery curve that you can see here to the right, showing you where you can operate with the different Jameson cells. With Jameson cells, it is slightly different in design to a conventional circuit, where if we understand the grade recovery, where you want to operate on that curve, we can easily design the cell knowing that we need to know your volumetric constraints and the test work. We've also seen a lot of interest of late in silica flotation. There's been a recent boom in magnetite projects. As more magnetite projects are kicking off, we found that there's been increasing need to understand silica rejection from the magnetite cons. So a lot of this reverse silica is coming up. Unlike the previous example where we used a J300 pilot rig example, we actually have dilution cleaning that I've got on the right here to show you what the Jameson cell is capable of. The dilution cleaning procedure is a lab-based procedure that anyone can do on site and is a bit of an entrainment test. This allows you to understand whether a Jameson cell would be suitable for your process. If it is, you can take it further and ask for piloting at a laboratory or an on-site piloting by an L500. But what I do want to stress is something like magnetite, it's highly important to make sure your sample is conditioned. But as a rough rule of thumb, if the material is conditioned, liberated, the Jameson cell will recover it. Now, moly. There was a comment on the previous slide that moly is something that's been largely of interest of late, and it does make sense with how all these battery metals are headed. We put a Jameson cell on a tails of a column. Typically, the design would be before a column at the head of the circuit, but in this case, we put it on the tails, and we put a Jameson cell primarily to recover copper when this project was done. When we look at the mass balance from all the surveys that were conducted, we found that the Jameson cell was particularly capable at recovering moly versus the traditional column design. As you can see here, when you take the Jameson cell and the column together, the Jameson cell actually recovers more copper than the column, even though it's treating the tails of the column, and significantly more moly versus the column, which is a no-brainer and why people were so excited about this when we got these results. As you can see, it's the fast kinetics of that downcomer that really drives this, and why the Jameson cell has been so successful in these copper moly applications. Lithium is another thing that we've been seeing a lot of interest of late, and I put a dilution flotation test here just to show you what some of the stuff has been capable. And here we ran lithium as a cleaner. We found that we could achieve about 5.7% lithium oxide grades, around 82% recovery. Key things here to make notes of: with the froth washing will maximize your grade, i.e. get rid of all that entrainment. Your final grade is very dependent on mineralogy, as you'd expect. And there was very good potential based on other light minerals to upgrade the lithium from about 1% to greater than 5 in a single stage. This site was interested in some of our work, and there is further test work required in rougher applications, but what I really wanted to identify is some of the potential that this technology can do for you in these applications. Now, I've told you that we've been working in new applications, but another key point is how to actually get my Jameson cell there. And what we've done is we've developed a whole series of modular cells. Pretty much any version of the cells we produce can be supplied in a modular segmented fashion to help suit remote and transport restricted applications. These cells, I'll show you, can be separated. This is a B cell design, and as you can see, the cell itself can be split up into 5 key components, allowing you to transport it in small pieces around the world. Now, all right, so we're working in new markets. We can now move these cells around the world. So I've already said that the Jameson cell, if it's treated, liberated properly, it will float at then why don't you actually put the whole set of cells together and do it in a concentrator, which is what we've done. We found that the Jameson concentrator is something that has really taken off of late. It can be used in all flotation applications from, as I mentioned, your roughest scavenger cleaning circuits. When we tie it with our isomol technology, we can actually create a very low footprint, low capex, less OPEX style design. It's less OPEX because you don't have the agitators and amount of pumping that you need. When you put this all together, you get about 40 to 60% less footprint, significantly less power, flexibility of the Jameson cell, and it is low risk and a high performing technology. So, i.e., the Jameson concentrator takes the best of the cells and makes the most compact product going around on the market. Now, I'd like to talk to you about Jameson cell fundamentals and test work. This is a very interesting area, and we'll highlight some of the key things that you need to be aware of on the Jameson cells and how you can take that to a test work level. Key components will be what's happening in the downcomer, different cell designs, and the control philosophy on how they actually operate. Now, this is a Jameson cell here. We have our main components are slurry and air distributors, slurry isolation valve. I'm going to skip these. The Jameson cell itself, I'll go through the whole cell itself in a little bit more detail, but the downcomer is probably the key defining factor. When the downcomer is the magic of the Jameson cell. When you pump slurry into a distributor, what we do is in these downcomers, we actually focus that jet slurry through a orifice. That orifice creates a jet, and that jet will basically be sealed off from atmosphere, and as it goes through the orifice, it actually starts to create a vacuum, and you find that slurry starts to rise up in that downcomer. The jet will plunge into the surface of that slurry, causing the entrained air to shear into fine bubbles, and so you don't need any blowers supplied. That air is controlled from atmosphere with just a basic butterfly valve. This high intense mixing creates really high probability of bubble particle contact and collision. And it's this forced contact that actually allows us to size these away from residence time. And we only need to look at the grade recovery curve and volumetric flow. Residence time, if you want to be exact, is probably only a few seconds in these downcomers. But that's all we need because we've already enforced that particle bubble contact. Once it leaves the downcomer, your concentrate will float, go over the launder, and while your tails will have a small portion sent back to basically ensure steady feed flow to the downcomers. By having the steady feed flow, you know performance is always going to be right, exact, and it's always going to behave in a good manner. Now, this is a video of a coal cell with a poly downcomer, but I feel it's really good because it actually shows you what's happening in these downcomers, and this scales up all the way to the full scale installations. As you can see, it's very turbulent, very intense mixing, and that's what makes sure that you get that particle bubble contact. The position on where the slurry and mixing zone happens is a function of how much air that you're letting in. So since this is close to the top, we're limiting the amount of air we're adding. If you want to move that further down, you add more air. Now, we have a tails recycle mechanism, and the functionality of this has basically been designed to allow the downcomer to operate with a constant flow rate. When you have cleaning circuits, you know rougher mass pools can vary. By having a percentage recycle, you ensure that stability always happens. It has the ability to increase recovery as it allows unattached particles and other pass through, but it's not the primary function of why it exists. It is for that process stability. Every process, we actually design a recycle percentage in, and what that means is if I have a 30% recycle, that means 30% of the volumetric flow rate through that downcomer is tailings, 70% is fresh feed. These changed on different applications. If you're looking at rougher scavenging, it can be anywhere from 20 to 30. Cleaning duties can be anywhere from 30 to 60% recycle. The control is not applicable. You don't have to do anything special. We already have this built into the plant design. Now, this is a E-cell, and I'll explain how the cell works, and you'll get an idea of the control. Now, this is the feed pump box highlighted where the new circuit feed is added. At the bottom of that, we would have a feed pump, and that feed pump would pump up to the downcomer and provide a slurry head pressure of about 150 kPa. The slurry will go through every downcomer, and it's not like a cyclone pack. We operate with them all open if we can, and go through these orifices that you previously discussed in the downcomer. Once that jet forms, we will draw air from atmosphere through this black line here. That slurry mixing happens in your downcomer, and then what will happen is after you force that particle bubble contact, it will come into the flotation vessel. Your concentrate will rise up through the wash water being added and collect over the lip down the launder, while a portion of tails will get recycled. In the E-cell, we have a recycle slot at the bottom that will actually control how much we're flowing back to the feed pump box through hydraulic head, and we control a dart valve to allow our tailings out. This is pretty much the function of control. We monitor a lot on the cells, but it's relatively simple. We monitor froth levels, air levels, wash water levels, and we can add reagent to the feed pump box. On the Z cell is an interesting model. It's a combination of a B cell distributor with the E cell recycle mechanism. Fundamentally the same, but still worth addressing. We add new circuit feed here to the feed pump box, and then from there we actually pump it through, up through the bottom to your distributor. Goes through your distributor, through here, draws air from atmosphere, goes through your orifice, creates a highly intense mixing zone in the downcomer, enters the flotation vessel, concentrate floats over the launder, down and collects the concentrate, the tailings goes through your recycle slots. The recycle is physically built into the E and Z cells. There's nothing fancy that has to be done, and it is, like I said, works on hydraulics and hydrostatic pressure in the flotation vessel. The head pressure will always be higher on the float vessel side, which will push slurry through those slots, and we control and size them specifically on every application. As your feed flow will decrease, the level in the feed box will decrease, and through the recycle slots, there's more head pushing it through, and this causes the increase and maintains your level. One of the things that's actually quite interesting is it actually allows you to run your cell on 100% recycle if your plant went down, which is quite useful in other applications. Say if you're starting your circuit, you can start them up on water, run them on 100% recycle, and then start to add slurry in a more controlled way. And like I said, the slots are suitably designed to meet the requirements of the cell sizing. Now, for control, we have those 3 levels of control as we've mentioned. We have level control, so we have hydrostatic pressure probes that will measure your froth depth, and we have 2 in there to manipulate for density change, and this helps us control the recycle. We have air. Air is a very simple control loop. It's measured, controlled to an operator input, vacuum's measured, and we just change an open and closed butterfly valve. And wash water control, we measure how much water we're adding, and then get an idea of how it looks in the field. B cell, how it works is fresh feed will come into the Jameson Cell downcomer feed hopper, which is external. It will then pump up through the bottom. So B stands for bottom fed, up to your distributor. We'll go through all your downcomers, individual downcomers, have that intense mixing with your air, enters the cell, and then your con floats over your launder. The tails will exit the cell, hit an ERM. The ERM stands for external recycle mechanism, which will basically be a dissipation plate to take off the velocity and then have an overflow launder. That overflow launder controls how much you send out to tails. A portion of the tails is always recycled back to the Jameson cell, like I said, to maintain that constant downcomer feed flow and level. The remainder of the tails flow over the ohm weir is actually the true tails product, and that is transferred to the next part of the process, i.e. whether you have a scavenger. So now the recycle here is external, and I think this photo probably shows it best. As you can see, your flotation vessels here, tails from here will actually come under into the ohm, hit that dissipation plate, and a part will recycle back to your feed pump box. There's an overflow weir that will then take it to the next cell. One of the things that I do really want to mention is any feed that goes to your feed pump box will never short circuit the process. Everything in that feed pump box has to go up the distributor and through the cell. I just want to really stress that. There are two outlets on the ohm. We have one with a control valve, which controls how much you're sending back to the feed pump box, and the overflow weir, which sends it to tailings. We try to maintain that steady volume, which is one of the key operating principles of the cell. Now, going through the B cell control, it's exactly the same measures, just slightly different format. Level control is done through hydrostatic pressure probes to measure froth depth. Butterfly valve at the bottom of the cell is done to manipulate level. The air control is measured exactly the same way. Set point butterfly valve controls how much air you want to let in whilst getting an idea of vacuum. In typical applications, your vacuum should be anywhere between -20 and -10 for most Jameson Cell operations. And you have wash water. The wash water is just measured and controlled depending on operator input. In an ideal world, you just want to have a good thin coverage across the entirety of the cell. And we have that recycle control where portions of salines is recycled to maintain that level. Now, I've touched on how the cell itself operates and the relative simplicity of the control of it, but I do want to touch on some of the OpEx stuff associated with the cell. The only moving part on these cells is the feed pump box. So your pumping requirements on a per cell basis will likely increase, but it offsets significantly especially when you start putting these together in multiple cells. There are no mechanical parts, like I said, other than the pump, no blowers, no compressors. And when you look at the cell design, you're typically looking at about 30 to 60% reduction in power. Anyone who's particularly interested in this, we can discuss more, but that is a rough rule of thumb for you. Maintenance, we can do everything on the run. There's only two parts that may wear, and that's the slurry lens and the ace valves. To replace these, it can be done on the run. You just isolate the downcomer, open it up, check that and then check whether there's air being drawn in, which identifies whether there's a blockage, or check whether here the check valve is missing. And to be fair, some of these parts last up to 30 years, which was a bit of a surprise. So it's not really a high wearing item either. By being able to do these on the run, you can reduce your labor costs because you don't need that many people there around, and it actually reduces your storage and spares holding. When you do rough maths in some of our case studies, you can see about a 20 to 50% reduction in spares holding. And now the part that actually is probably a good highlight is in cold climates where buildings are heated, unlike Australia, everything's outside. If you have to heat a building, you want to make your footprint as small as possible. You put a large number of these Jameson cells together, your footprint shrinks considerably, which actually lowers your CapEx costs significantly. And that's something we're really quite proud of. And just for reference sakes, I always like having these about. It's just a good reference. And we'll send you the slide deck with this. What cells we have, the volumetric max flow, and the size of the downcomers to give you an idea of the throughput capacity. I do want to mention, since this presentation, we actually have developed a larger B cell, the B10500-16, which can take up to about 2,000 tons per hour through a single unit. Now, test work. I'd like to go over test work, and in this area, this is something that's really, really important to me. I'd like to really highlight the benefits of the three-stage dilution cleaning test, i.e. an entrainment test, go over some of the lab equipment that you have piloting, and a very quick intro into how to actually interpret some of these flotation results. Now, there are a range of options available for testing Jameson Cell application. What I do recommend is if you want to know whether a Jameson cell might be suitable, just do a 3-stage dilution cleaning test. We have lab Jameson cell apparatus tests as well, and you can do on-site piloting, but always the first step would be that 3-stage dilution test. The test itself is simple, easy. It can be on any flotation cell, any Denver, because it uses conventional bench equipment. The purpose of the test and the fundamental understanding behind it is more of an entrainment style test, and it basically shows you the effect of reducing entrainment. It's great for most applications, will supply meaningful data, and we actually have offered process guarantees on these tests and from the small sample sizes that have been used to make them. The test itself is pretty simple. You run the first portion of the test and like you would any conventional test. So if you had doing this test in a rougher application and you've rougher around for 10 minutes, in this case, your first cleaner would be the exact same, so it would run for 10 minutes. You take that con, you dilute it to around 10% solids by weight, sometimes in a smaller flotation vessel, float that again for a time period ref to the first cells, and then for the third test, you take that con and then you do kinetic samples. So i.e., by taking the concentrate, diluting it further and moving it to another test, you're just trying to reduce all your entrainment losses. By doing this, you can actually plot a series of data points on a grade recovery curve, which we have done here in green. And that shows you your theoretical operating of a Jameson cell. And then the orange dots there are the actual surveys. And this is a scale up from a full scale installation compared back to the dilution cleaning test in a cleaner scalper application. The 3-stage dilution uses the small lab cells that make small bubbles and have high shear environments, which reflect the shearing effect within the downcomer. Things you have to be aware of is you use frother about 15 to 20 ppm, which is that triple C point, to ensure that the fine bubbles are sustained and simulates what you see in a Jameson cell. The dilution cleaning simulates the wash water and that entrainment reduction, which I've touched on, and it does have proven scale up to the full-scale Jameson cells. And here's another example on the right. These results from the grade recovery curve can allow us to select the equipment operating points, size equipment, allow us to benchmark, and we'll provide the foundations of performance guarantees if you were to get a Jameson cell based off one of these tests. But like any test, there are limitations, and it's always good to understand what they are. It is a good benchmarking mechanism, but it still uses the conventional cell mechanism. In something like gold, that high shearing effect and surface cleaning action can actually cause performance to be much better than the test, and we see this in certain minerals. So the test itself in these will be the minimum that you would expect, even though actual performance could be better. And there are chemistry limitations. Here, what we did was a kinetic single-stage test versus the 3-stage dilution cleaning test. And what you could see is there's almost a limit on the recovery in the 3-stage dilution cleaning test and grade. What actually happens is highly reactive sulfides will change their kinetic performance through the cleaning stages. So you have to maintain EH and pH. If it's not looked at, you may get these unusual curves that do not actually reflect actual performance. So just be wary of EH/pH when performing the test. We have these lab Jameson cells. We have the L150s and J300s. These actually simulate that downcomer. It's an actual Jameson cell with the same size, same ratios for all the downcomer sizings. And this actually allows you to benefit using an actual Jameson cell. We do these in a batch test or pendulum test or continuous. We produce graded recovery curves in each batch test and can be run continuous to get that real sense of confidence that it works for clients. And luckily, you don't need too much for these if you were to do a batch test. You'd need about 20 to 50 kilos depending on the test type that you want to conduct. And in Canada, particularly, since this is a CMP course, we have these L150s at XPS, SGS Lakefield, and Carem and there are a few more coming around the country, which we're working on. Now, the L500, these are the rigs that we typically send to site, and they're used for plant operations. These work really, really well. Like the L150, these are based on actual Jameson Cell dynamics and advantages, and allow you to do a continuous process. We have an integrated recycle to help simulate that process stability and can handle feeds from about 3 to 8 cubes. We send these all over the world, and we do these as rental units or as individual purchases. But the main fundamental difference of piloting is we actually run a test matrix when we get them to site. This is done to allow you to understand the operations and conditions to get you the best out of a Jameson cell if you are going to proceed. To do this, we use a structured survey matrix to test the best variables. We collect samples, compare results, and then basically fine-tune to the ideal conditions. I.e., the purpose of these tests is run on an L500, where you're allowed longer continuous runs at ideal conditions to help build confidence with the technology with people on site. We can produce grade recovery curves from every test. Grade dilution cleaning allows you to identify how you're going to operate your Jameson cell. Lab and pilot results will result directly to the full-scale cell. On the right here, we've shown how the dilution cleaning test scales up to the L500. We know the L500 scales up to the full-scale cell. So we know whatever test we do, it will replicate performance of a full-scale cell, assuming everything is done correctly in the test. Now, I've done my dilution cleaning test, and all right, I got my curve. How does that actually reflect to a full-scale cell? And so what we have here is how we'd actually break up the results and how you'd actually test it. In this example, we have a grade recovery curve where the site's final con target was 27%. As you can see, some of the points are actually higher than the target grade. Some are operating around the actual point, and some points are way below your final target. So in this case, as you can see, up to about 60% copper. All these points show that you're achieving grades up to 30% copper. In these applications, you'd look at maybe putting a rough scalper in, because that would help you debottleneck, remove your copper units at grade, and allow you to design everything past that point a bit smaller. Where you're actually close to your final con target, you could put a rougher in. The rougher would help chase recovery and also help operate around that target point. And the last there we would do as a scavenger. And the fundamental change between all these points is how much air we're adding, wash water, whether we've got lip extenders or froth grouters, and that helps us optimize the cell for every duty. Now, Adam will take you through the next series of slides, and I'll pass it over to him.
As Scott mentioned, I'll probably be presenting for the next maybe hour and a half or so, or a touch shorter, looking at some of the key operating factors for the Jameson cell. So this is both in terms of some of the key things that are important for making sure the Jameson cell is running at its most efficient, but also some of the key benefits you get from the Jameson cell and how it operates to produce effective flotation performance. Then I'll also have a look into Jameson cell sizing. So having a look at some different cases there of how we size individual cells, what we need to look at, what it's based off, as well as touching on some of the more full circuit scenarios or circuits with multiple cells as well. So with that being said, I'll jump straight into it. So during the first section, which will be the key operating factors, the key topics I'll look at are air and vacuum pressure, and I suppose the balance of those two operating items. The froth washing, bubble size, and the importance of And I'll touch a little bit at the end on flotation kinetics and the difference, I suppose, with the Jameson Cell in terms of kinetics and how concerned we are with kinetics compared to things like your conventional mechanical cells. So firstly, having a look at the vacuum and air pressure. So vacuum plays a vital role for a few reasons in the Jameson Cell. As everyone's aware, it's a pneumatic cell, and we generate the vacuum within downcomers, which is what gives us the ability to draw air into the system and not need basically blowers to do that. We're able to bring it in through the atmosphere. But there's a couple of other key things that play a vital role here. So what the vacuum also does is it actually dictates where the level sits within the downcomer. So with the air valve fully shut off, basically the level in the downcomer, the slurry level will rise up the downcomer basically right to the top of the downcomer. And as soon as you let in air to the system, the level will gradually drop off the more air you introduce. So when it comes to operating, it's important to then maintain what would be a minimum sort of vacuum. So as a really good guide, we suggest that you need to run with at least 5 kPa of vacuum still in the system. Dropping any lower than this would result in the slurry level getting too low in the downcomer. And this can result in basically a transfer of the mixing zone from the downcomer into the tank. You obviously lose significant efficiency in bubble particle interaction when that occurs, but also you see turbulence in the tank and disruption on the froth surface level, which can obviously impact froth breakdown and those sort of things. Anywhere probably between -5 to -10 kPa is probably more so what we'd call a bit of a danger zone, or a zone where you would want to be monitoring closely visually in the cell. Some applications can run down to as low as sort of 7-8 kPa, particularly specific duties like coal, where we're looking to really maximize the air. But it's getting to probably a borderline position, and it can depend on other factors within the system of how far you can push that vacuum before you may see issues with transferring the mixing zone into the tank. Anything above that 10 kPa is basically fine for operation. And it should be in a good basically scenario for maintaining that mixing zone within the downcomer. We suggest that anywhere between 10 and 25 kPa is the ideal zone. This would mean that it's sitting basically in a zone where it's obviously not too low, but it's also not right up the top of the downcomer either. And as I said, you've got plenty of room there for mixing zone, as well as some improved probably area to dissipate some of that energy as the material moves into the main tank. So we still recommend that air is obviously the main control in the system. And I'll probably say there as well that even if there's a need to run still with the higher vacuums, anywhere up to sort of 30 kPa, really low airs, specific for a duty, that's still fine. The only thing that would need to be probably maybe checked a bit is the ACE valves and some of those simple operational checks, just to make sure that there's no sort of slurry buildup occurring in the airlines or anything like that, because as I said, your level will be right up the top at the lens level and the ACE valve sort of level. So that's the only thing that needs to be checked. The operation should be fine. And as I said, air is still the main control. You still want to be adding the amount of air that you need to create the performance that you want and sit on the grade recovery curve where you want to. There is the occasional operation and scenario where controlling by vacuum is an option. Usually it's more in those scenarios where you just want to drive to a maximum air. So it may be understood where the vacuum can be pushed to get maximum air, and therefore you can set up the control to operate to target that vacuum and essentially get the maximum air you want. So now just having a look at entrainment within, I suppose, any flotation system. And then I'll discuss obviously how the Jameson Cell is effective in reducing the amount of entrainment you see to your concentrate. Basically, the key principle of this is that bubbles actually carry a water wake with them when they're rising to the surface. And it can be this water wake which you'll potentially get actually some more of the target metal or material that you want that gets dragged up with this wake. But often you get quite a lot of gangue or unwanted material as well that gets dragged to the surface. What ends up happening then is when the concentrate forms is you'll get the pockets of water in between the bubbles. It'll be nicely now compacted and obviously starting to form a nice froth concentrate. And those gangue materials, those fine gangue particles will be caught up in between the bubbles and will essentially come over across to the concentrate launder unless basically there's something's done to stop that from occurring. So in the past, basically it was accepted that it was a fact of life that you would get entrainment and that water would be recovered, and that essentially we would just have to deal with the gangue that came across with the water in maybe other ways with multiple stages or other techniques that occurred. But essentially the theory came about of obviously trying to replace that water that was coming up in the concentrate with basically new clean water and suppressing that entrained material that's been caught up back into the slurry. So this is what we've done on the Jameson Cell. You can see the photos on the right-hand side there of examples of our wash water system. And as I said, the aim there is obviously to replace all that water that's been contained within the concentrate and push that back into solution. Here's just a good example from a pilot rig of basically a material. The concentrate or the target material to produce was a white concentrate, but the gangue was very clear to see, being a dark brown product. And without wash water on, you can see all of the entrained material caught up in that concentrate. And then once wash water was added to a sufficient level, you can see the difference in quality in the concentrate. And so this is an example of what can happen in terms of the grade recovery curve with the impact of having wash water compared to not, particularly when you're talking about feeds with really fine material. and this is an example of, say, a Jameson Cell performance with showing the Oris and what would be possibly a conventional mechanical. So you can see a significant upgrade in the concentrate for a large portion of the recoveries, basically until you're starting to get to those extremely high recovery points of effectively just mass pulling. So it makes a significant difference and means you can reduce the amount of stages you require to get the upgrade that you need. This is a short video just showing the wash water. I'm not sure if it'll come across well. Actually, if it wants to play at all. Might be a little bit jumpy. It usually is coming across from sort of Zoom, but you can possibly get ending of seeing how the wash water sort of works on the Jameson Cell. Very jumpy. That's all right. We'll skip through pretty quick. It was just a very short video, and you can obviously, if there was anyone interested later on or something, you can show them live, I suppose, whilst you're there. But a few other key things on wash water with the Jameson Cell in terms of our particular design. So we use the tray systems. We have a couple of different versions of the tray systems now for ourselves. So we have options for removable poly trays that can basically be taken in and out and cleaned away from the cell. We also have full stainless steel trays that have been pre-installed within the cell and have matting sections on the bottom that can be taken in and out and washed when required. So water will come in through a common manifold, and each tray will be delivered a specific offtake of water from that main manifold. Obviously, we specifically design the cells, each of the cells, for a specific duty. So there'll be a large number of holes with each cells, could be anywhere between 4 to 6 millimeters in size usually. But as I said, we actually do specifically design for each Jameson cell for the duty that's going to be completing. So we want to make sure that the holes we design in terms of number and size will be effective for the wash water rates that need to be run on that specific cell. So we tend to size for a neutral bias, which essentially means that we're looking for the a 1-to-1 ratio in terms of the wash water to the water that would be basically collected or brought to surface in concentrate. And that's obviously based on fully replacing that water to make sure that we've got 100% sort of new clean water within that concentrate, and all of those entrained particles are pushed back into the system. It does depend a little bit on the duty and the commodity of how much wash water is required. As I said, particularly if it's a very fine grained material, possibly if it's a high feed percent solids, there may even be some benefits on going slightly higher than a 1-to-1 ratio. And there's other scenarios where you need hardly any wash water at all if it's maybe a coarse feed, and you're less susceptible to obviously getting those entrained particles. And obviously there's the ability to add more or less sort of as required, and is something that usually is looked at during the commissioning stage of what's the most effective amount for the specific duty. So bubble size is another thing that It's very important when it comes to the Jameson Cell performance. And it's pretty widely known that it's an important factor when it comes to anything to do with froth flotation. It's been shown that obviously the finer the bubbles, the better place we are basically to collect all the material, and particularly that finer material that could be in the feeds that we're trying to treat. With larger bubbles, you obviously get limited contact with some of the bubbles. There's less efficiency in terms of a per air basis, which there's sort of a slide on coming up shortly. And they also tend to very quickly and more susceptible to coalescing, which will create sort of turbulence, and you'll get particle drop off and those sort of things occurring. Oops, skip too quick. So obviously the Jameson cells produce very fine bubbles, which are generated within the downcomer in that high shear, high intensity mixing zone. And that's what's really effective in creating and generating those small bubbles. And it's also the place that they're obviously the most effective within the Jameson cell, being the contact zone. So why are small bubbles important? It's a bit more sort of here, and this is just looking at some comparisons from a study done at one of the universities in Australia a few years ago now, showing sort of the bubble size of the Jameson cell, which is in red there, down the bottom of around about the 0.5 millimeters in size, compared to anywhere between 1 to 2 millimeters in size for maybe conventional cells. And the columns that were tested there at the time were even a bit larger, at around the 2.5 to 3 mil sort of range. And this diagram on the right just explains a little bit why bubble size is important. So not only we were talking about before how bubbles actually drag water, a wake of water to the surface, but when they're moving up and through liquid, they'll actually create a streamline around them as well. So as the bubble's moving through your pulp solution, you'll actually get this water streamline around the outside of the bubble. And this could show, if you have a large bubble, what can happen if you have coarser material or finer material. And so material that's coarser can potentially be okay, because the bubble will be moving through the solution and the particle will be big enough essentially to overcome the gap between the streamline that moves around the bubble. But if the particles get too small or on the really fine side, like you can see the bottom right there, that deviation of the wake or the streamline outside the bubble actually may be too big of a gap for the particle to actually ever come in contact with the bubble. And so it might end up becoming extremely difficult or virtually impossible for That's okay. I think basically nearly got my point across for this slide, but essentially I was just mentioning that the bang for your buck in terms of the air addition is obviously significantly improved with the smaller bubbles as well, with the surface area. So this is an example of where small bubbles basically have been shown of how effective they are at recovering the really fine fraction. So this was a copper gold example on a Jameson cell in the field, and we're taking the basically -38 fraction and seeing at the different cyclone fractions what the recovery was. So even down to -C5 level, which I believe is into your sort of -6 micron range. the recovery of copper and gold was still really good at sort of 80 and 70%. But a key one as well there, when also looking at wash water, was the recovery of the entrained NSG, which stayed really low all the way to the fine particle sort of ranges. So these sort of results show not only the impact of the small bubbles, but also the wash water on the Jameson Cell. So now just talking a little bit about the importance of frother, because this actually goes hand in hand with, I suppose, the Jameson Cell's ability to produce fine bubbles. So essentially the Jameson Cell, no matter what, it will produce fine bubbles. That high shear mechanism that occurs within the downcomer will be really effective for creating the fine bubbles. But essentially they'll be lost straight away if frother's not in the system, and the water chemistry basically isn't correct. So frother plays a vital role in maintaining those fine bubbles that are created and avoiding any coalescence and basically losing the benefit of what the Jameson cells produce. But not only does the frother play an important role in maintaining the bubbles, it also plays a secondary role in the Jameson cell, which can also be equally as important, or probably at least as important to that, and that's creating a much more stable and sort of consistent air to vacuum ratio. So the frother, with its ability to improve the liquid chemistry, the surface tension, plays a vital role in being able to maintain your vacuum for longer, whilst basically bringing in your higher air ranges into the Jameson cell. So not only obviously important for basically any Jameson cell operating, but particularly the situations where air is going to be pushed to the higher limits. And this will create a scenario where, as I said, you're holding that vacuum for longer, and you're not at risk of transferring that mixing zone, which we talked about earlier, into the tank. So having a look at an example here, and this is touching on, probably just going to have a look now at some comparisons a little bit with the impact of residence time compared to mechanical cells, for example, compared to Jameson cells. But this is also a good example of, I suppose, those different particle zones and how we see the difference with recovery over those zones, particularly for entrained material. So this is just highlighting a chalcopyrite float in the laboratory and the impact of residence time on recoveries of the target material. So as you can see, particularly in the fine and coarse end zones, at only half a minute, the recovery is very low of your fine and your coarse material. But your recovery improves through all the zones as you float longer, which clearly makes sense in a mechanical cell. The longer you float, the more time you give for it to recover material. But what's also interesting then is looking at the gang material, which are the dotted lines now on the graph, which the recovery also increases for this as your time goes along. And it's particularly evident in that sub 10 micron range, which, as we've just spoken about, will of course be due to entrainment that you'll see coming to concentrate. So the more that you obviously try and pull those last bits and pieces of the target material, you'll also pull much higher gang material into the system. So in terms of, for a Jameson cell, in terms of recovery of particles by size, this is an example showing that it's very effective at both the fine particle range and all the way up to the coarser end. So anywhere from sort of the 3 micron range all the way up to the 300. And in this example, this was a copper flotation circuit, actually in Mount Isa, where we saw even 93% recovery at that 3 micron range, and still 97% recovery at the 300 micron range. And it was only once it got to basically a particle size where you would see particle drop off in your froth phase that the recovery started to drop off. So it would be in line with mechanical cell or any sort of your other conventional flotation cells, with that difficulty with the coarser material in the froth phase. So what makes it really effective over this range is the high void fraction area within the downcomer, and we'll have a bit more of a look at that in the next couple of slides. So one of the big benefits, as I said, is that with that high intensity mixing zone within the downcomer, is particle bubble interaction is virtually instantaneous. So when it comes to residence time in comparison, the interaction of bubbles and particles virtually instantaneous. So residence time doesn't become an issue for Jameson cells like it does where there's a higher or you're relying more on probability of bubble particle interactions like your mechanical cells and other flotation devices like that. And as I said, this then becomes very effective at the collection again of both fine material and coarse material, and it's that combination of the small bubbles and the high void fraction area within the downcomer. So when we talk about void fraction area, essentially what we're looking at here is how many bubbles are within basically a specific area. And the pictures on probably the right here show sort of an example of what we would mean when we're looking at maybe conventional cells compared to Jameson cells. So with mechanical cells, as I said, there's a lower void fraction area, meaning per area of slurry, there's going to be less bubbles within that particular zone. And so particles moving through that area have less probability of actually seeing a bubble as they move through. Whereas within the Jameson cell downcomer, you're talking about everything moving through very small sort of volume, sort of small surface area. And the air to pulp ratio is extremely high within these small zones, and there's basically significantly more bubbles sort of per section of slurry volume, and therefore the chances of your particle seeing a bubble, as mentioned, is essentially 100%. What this means in terms of residence time and kinetics is that kinetics are obviously extremely fast within the Jameson cell. To sort of show in comparison to often in, say, laboratory mechanical cell tests, a very common test would be to complete a recovery over time graph, similar to the one on the right, where basically you would establish a curve of over time how the recovery improves through the cells, and this would be also reflected if you're operating full scale sort of for mechanical cells. Whereas for Jameson cells, the reason that we can operate with fewer units is because of what we just talked about, and that very quick bubble particle interaction and the very quick kinetics, which means that we can recover to that target recovery in basically a single unit or a couple of units. Essentially, within the first unit, if a particle wants to float and it has the ability to contact a bubble, it will contact a bubble immediately. So now I'll move into having a look at equipment sizing. So in some ways, it's a good sort of section to transfer into after talking about sort of kinetics and resonance time through Jameson cells, because this section will look at then what becomes our key criteria when we're sizing the cells, and what are the main things, as I said, that become important for making sure we have the right cell selected for individual duties as well as circuits. So a couple of the areas we'll look at carrying capacity and volume throughput. And then, as I said, we'll touch on just a short amount with when it comes to full circuits or Jameson concentrators, what extra we obviously have to consider for those rather than just a single cell. So there's a lot of writing sort of on this slide, but what it's just looking to display is what's basically this is showing what's the minimum requirement of information we require for sizing for a cell. So it actually looks a lot, but it's not a huge amount. So I mean, obviously we need to know the commodity and what the duty is going to be that the cell's performing. And then the key information really comes from some of the feed and the concentrate data. So particle size is very important. We'll explain a bit more about that in a minute. If there's been a particle size distribution done, that's the best scenario, but we also have an extensive database of sort of standard particle size distributions for certain P50s or P80s or P90s. So even if just a P80 is known, then this is fine for us to understand what typically the sizing would be over a PSD. We then also need the dry feed rate, as well as either the percent solids or the water addition in feed. What the target metal feed grade will be, and the solids SG, both for the feed and the concentrate. And then simply what the expectation of the cell is. So what grade's going to be achieved for the concentrate and what recoveries are going to be achieved. So typically this would hopefully be done by either lab or pilot tests for specific Jameson cell tests, but we can also utilize conventional mechanical cell laboratory tests as well. Other factors that are useful, not vital for the sizing, but can give us a bit more of an idea of what's required, or could impact that mass balance and that sizing that we do. So the SG of the wash water that will be being delivered can be important. We do obviously see some scenarios where obviously sites only have access to maybe to saline water, salt water, or even, to be honest, if it's known that the quality of the water is not the best, then we can incorporate that into the design. What the availability is of dilution water to the feed. This can be important, particularly for cleaning stages and these sort of things, where dilution water can play a part in the sizing, particularly for allowing for feed volumes. If it's known typically what concentrate percent solids will be formed, this can be important for your wash water addition. So again, targeting that one-to-one replacement of the concentrate water that's being produced. Flow sheet description always helps if there's any considerations that need to be made upstream and downstream for the sizing. Frother used can be useful for us to know. We've got a database now of frothers that have been used and worked well or not worked so well in the Jameson cells. So just gives us that initial basically conversation, or we can highlight any issues that may be seen with frother, or reagents as well, and pH. Footprint requirements. This can become important sometimes for sizings. So there's even occasions where we may need to go to 2 smaller cells than 1 bigger cells due to footprint requirements, and we can try and make sure that we can fit to a specific an area or something like that if possible. Height requirements are also important with the different designs we have with our cells. If any equipment's being replaced with this, that can be useful to know. If there's results from those previous equipment, that's useful. And of course, any pilot or lab test results that have been performed. For some niche applications, coal's an example. You may also look at some things a bit differently. So for coal, we use yield instead of recovery, and then ash content is basically used instead of a target metal, as sort of your ash becomes really that obviously key component you're trying to get rid of in the coal scenario. And then probably the most important thing is that we always size on a maximum or a design case. So we look to produce mass balances and obviously the complete sizings, and the key one when it is at this stage is the maximum or design scenario. And this is pretty obvious that you want to make sure that the cells selected can deal with what is going to be the absolute maximum scenario that the feed may present to the cell. So yeah, always important to have that number as well as nominal. Nominal is still an important, and we'll look at that to make sure the sizing solution still fits both scenarios. But this is probably the key one for design. So then when it comes to sizing the cells, in reality, it's simply based on 2 key requirements. The first of these is the feed volume to the cell. And again, this is where it's important that we look at maximum or design scenarios for the feed volume. And it's probably the easier of the 2 considerations. Because essentially in this scenario, we want to make sure that the downcomer capacity is significant enough to be able to take those maximum conditions, as well as having a target recycle range for the cell. So this is where we'll look at probably more so the range of operating scenarios for the cell, so nominals, minimums, maximums, that then we want to preferentially target specific recycle ranges. And essentially these recycle ranges are generally based on now the 430, 440 previous installations, and where we know cells operate well in terms of recycle for specific duties. And whilst trying not to obviously increase any pumping requirements where possible. Recycle obviously allows us to have that flexibility. We can also then utilize the slurry lens size if required to manipulate sort of the recycle range if required. But probably the most important is carrying capacity, which is the second thing that we need to check when looking at Jameson cell sizings. This can be much more complex scenario, and then part of the carrying capacity sort of family or group that we look into also includes lip loading, which is it's obviously the amount of concentrate coming over per sort of metre of lip on the cell. It's important that both the carrying capacity and lip loading is in acceptable ranges, or ranges that we know that the Jameson cells can perform. So diving a little bit deeper into carrying capacity, what that actually means. So for sort of people that aren't aware, basically carrying capacity is looking at basically the amount of concentrate that can be produced per surface area or metre squared available on the surface of the cell. So obviously each Jameson cell or each Jameson cell circuit, there will be a target concentrated mass that we'll be trying to achieve. And essentially the Jameson cells installed would have to have the enough surface area available to produce that concentrate. What plays a part in the maximum potential carrying capacity that can be achieved is basically, and it becomes different for every feed, and as scenarios change, there will be a different maximum carrying capacity achievable. And this is because multiple things play a part in that number. These include the particle size, the particles distribution, solids density, the superficial gas velocity, and the bubble size. The graph on the right here shows an example of what happens when you become carrying capacity limited. So this is looking at basically feed rate against your production of concentrate. And so as you can see, as the feed rate increases along to the right, for the initial parts of the graph, you get that steady increase in your concentrate, basically a 1-to-1 ratio with the feed rate increasing. But you get to a point where clearly the equipment becomes carrying capacity limited, and then essentially you get a flat line. So any increased feed rate to the cell past this point won't result in virtually any extra concentrate production. So it's just pushing feed straight to tail essentially. So this is what we want to avoid, obviously, in the Jameson cell sizings. I won't delve into this into too much detail, but essentially just wanted to highlight that the carrying capacity equation, or basically model, that we use has been developed on some pretty extensive laboratory test work. Essentially, obviously a paper was constructed from this research and was completed on both the Jameson cells and columns specifically. And it was basically looking at was the current industry-wide model that was being used working well for columns and Jameson cells. And it was sort of found that there was probably some errors in the model, or it wasn't good at predicting some scenarios. We actually found that to be inaccurate in some degrees for both minerals and coal, which were the two key things that were looked at. And with the older model, we saw it underestimated carrying capacity in coal, probably at the lower carrying capacity scenarios. But probably the more significant one was actually it was overestimating for some of the minerals or metals duties that we looked at in the higher carrying capacity scenarios. So that equation in the top right corner was basically what was developed to replace the old model and is what we use today. Looks very complicated, but essentially all those numbers are using based on those same variables we were talking about previously in the previous slide, which are things like your particle size, your particle distribution, your specific gas velocities, are all those sort of numbers in your bubble diameters. So to have a look at an example at this point, we'll look at what would be something fairly consistent with what we'd see with a rougher flotation here. And why we'll look at this one first is because this one in particularly is probably more a throughput limiting example. So in this scenario, we have 500 tonnes per hour of feed at 30% feed solids. So working off that, we've got a volumetric slurry flow of around about the 1,333 meters cubed per hour. So what we find to treat that amount of slurry flow, the smallest possible cell that we can do that in and achieve an acceptable recycle rate is with a B6524. So in this scenario, using this cell, we can get a distributor flow or a downcomer feed flow of around the 2,000 meters cubed per hour, which gives us a recycle rate of 33%, which was in that sort of target zone for the roughers. Potentially, for example, if this was on a maximum duty and the nominal was much smaller flow, we may be able to have a look at a cell size down depending on what that recycle rate sort of became for this maximum duty. But purely looking at these numbers, this would be the cell we would choose. Carrying capacity in this scenario was fine. Yeah, there was no issues at all with carrying capacity. As it's a rougher stage, tend to be low mass pull and higher volume feed scenarios. Now to have a look at an example which would more be looking at a carrying capacity limiting scenario. So this one we'll look at more typical, obviously a duty for a cleaner flotation cell. So in this scenario, we would look at a feed with an F50 of 9 microns. We'd have a solid density of 3.2 tonnes per meters cubed. And then looking at a feed rate of 50 tonnes per hour dry feed at 20% solids. That results in having a fresh feed flow of around 217 meters cubed per hour. So from this, using our carrying capacity model, we can equate that our maximum theoretical carrying capacity will be roughly 2.5 tonnes per metre squared per hour. The required duty of this cell is that we're looking to try and achieve 25% final concentrate grade with a 50% stage recovery. Therefore, our concentrate production is going to need to be 20 tonnes per hour. So having a look at the sizing, firstly, we'll have a look at the feed. and the throughput to see what we're looking at in terms of that scenario. So the smaller cell, we can fit that feed into and still have that 30% recycle is ends up being our 4 downcomer E cell. But then when we have a look into the carrying capacity, if we were checking specifically for that 4 downcomer E cell, that cell has a specific surface area of 3.3 meters squared. So then if we do a simple calc based on that maximum theoretical carrying capacity of 2.5 tonnes per metre squared per hour, it's just simply timesing that surface area by that carrying capacity to determine what our maximum theoretical concentrate tonnage production could be. And so in this scenario, using this cell, we can only produce 8.25 tonnes per hour of concentrate. As you can remember, back in the previous slide, in this scenario, we needed to be able to produce 20 tonnes per hour of concentrate. So the 4 downcomer E cell is insufficient based on carrying capacity. What we end up finding is our 12 downcomer B cell ends up being the appropriate cell for these carrying capacity requirements. So the B4512 cell has a surface area of 11.6 meters squared. And so again, using that same equation, simple equation of timesing the surface area by the carrying capacity, we find that this cell should be able to produce a maximum of 29 tonnes per hour of concentrate, which covers that 20 tonnes per hour requirement based on design. Recycle has obviously increased in this scenario, and the new recycle now is looking at 79.2%, which is up at the higher limits. So again, this was where it would come into be an important scenario of, is this the maximum duty, the nominal duty? Typically, as I said, we'd be looking at a maximum or design here. So if nominal scenarios were going to be much less, and we were getting in really high recycle sort of ranges, over 85% or so, we may look at using smaller lenses to bring that recycle rate down. So in that scenario, we maintain our surface area required, but we simply reduce the downcomer feed volume and hence the recycle rate. So carrying capacity, just in a way, doing a bit of a summary, combining the two key criteria. A Jameson cell is selected so that it has a volume capacity to be able to process the feed at an acceptable recycle rate, as well as B, has sufficient surface area to recover the concentrate required with respect to our carrying capacity model. The cell is sized correctly for the throughput, but doesn't have sufficient carrying capacity, then we need to move to that larger cell in order to be able to achieve those carrying capacity requirements. As mentioned, that'll result in an increase in percent recycle, which tends to be typical to have higher recycles within cleaner circuits and those type of things. As I said, we have some options for manipulations there with lenses. If we do find that it's an extremely high mass, so there's probably both two scenarios here. I was going to say, if we have a very low mass pull scenario, and the carrying capacity or the surface area requirements are very large, this is where we can look at things like froth creators and lip extenders to try and reduce the surface area and lip area. And as I mentioned previously, if we have very, very high mass pull, low feed scenarios, as I said, this is where we can look into things like smaller lenses. So now just touching a little bit on the extra things we like to look at when we're talking about full circuits or maybe Jameson concentrators, how that differs slightly, I suppose, from just looking at individual cells. Essentially, it's still based on those two key criteria of carrying capacity and feed volume. However, the only change that sort of happens a little bit here is that we essentially do things in two stages. We initially look at the circuit requirements in terms of carrying capacity and feed volume. So essentially that's what's establishing how many sort of cells we'll require to be able to cover the carrying capacity requirements and the volume requirements, and then breaking it down into individual cells. Commodity also becomes important in then designing the circuit and understanding the potential difficulties in, as I said, things like possibly losses to and froth phases and these sort of things, as well as understanding how many conventional mechanical stages of cleaning we're trying to replace. So we obviously base Jameson cells on an understanding that they can complete the equivalent of 3 stages of upgrading of mechanical cells. So this will often dictate if we need stages of Jameson cells or a single stage would be enough, sufficient for upgrading. We don't have to factor in residence time, as mentioned previously and explained earlier on. There's also consideration given to froth losses, as I mentioned before. So when it's things like roughers, we will always at least still have a scavenging stage as well to account for froth losses. There's also the experience we've gained over 35 years of having the cells operating and knowing effectively what cells can comfortably recover in each duty and in a single stage, and how different commodities affect that. As I said, generally we like to have, if we're having multiple Jameson cells in circuit, to have them in series, if possible, rather than in parallel. You get, I suppose, better selectivity of retreatment of tails by having series rather than parallel. And recycle rates are still appropriate in terms of trying to have the right amount of recycle for specific duties. Once again, always basing it on maximum or design scenarios. If anything, nearly becomes slightly more important for full circuits or full concentrators. As I said, we need to make sure that we can confirm that a circuit can complete the absolute maximum requirements that it could see. So looking at the different sections of the plant and then how we would look at sizing for these specific circuits. So for the rougher scavenger circuit, we would be looking to see firstly if a rougher scalper can be installed at the head of the circuit. So quite often Jameson cells can produce a final concentrate direct from flotation feed at a reasonably high recovery. So through test work, if we find this can be achieved, then we would always obviously start off with the rougher scalper. This takes obviously the load off the rest of the circuit and means you can reduce the capital requirements for the remaining circuit. And then typically we would have at least 2 to 3 cells in series, either scalper rougher. If we have a scenario where the first cell we know has a high recovery, 70 sort of plus recovery, and it might be a low carrying capacity scenario, maybe something like gold, where we're going to have basically a heavily sufficient surface area available in 2 cells and there isn't a need for 3. But we'll go to 3+ cells if it's a large mass pull requirement. And obviously we'll continue to increase the cells if they're required for carrying capacity requirements. And as I said, we always prefer to at least have those couple of stages purely for any froth losses that may occur in the first cells. We would then also jump to having additional trains. Our biggest cell now is the B8512, which John would have spoken about earlier. So if we end up with a scenario where feed volume is too great for this biggest single unit, then we would look at multiple trains or multiple lines. Can also occasionally be a preference of the client to have multiple lines for either a ramp up scenario or operating at different sort of capacities at different times. For the cleaner circuit, it's probably a little bit more complicated than the roughing circuit, but essentially probably the very first thing that we look at is how many Jameson cells are required to achieve the desired concentrate mass. So again, that's going back to that carrying capacity, and essentially, as I said, what surface area based on the Jameson cells is going to be required to be able to produce that design or maximum target concentrate mass. We also look at then how many stages of conventional mechanical cell upgrading are we looking to achieve. This can be obviously found out by doing Jameson Cell lab tests, or as I said, we can even base it on mechanical cell lab tests, or obviously pilot testing as well. And then we would make sure we've got sufficient Jameson Cell stages to be able to achieve that upgrading requirement. And then we would have a look at the scavenging requirements as well within the circuit. So scavenging circuit may not be required if, say, the upgrading requirement is very low or very easy. Again, maybe something like gold could be a scenario where you may not need scavenging because of the low upgrading requirements at that stage, and the quite easy ability to hit high recovery marks with the target concentrate grade achieved. We also look at the rougher scavenger, whether that can be used as a combined scavenger and it makes sense for that specific duty and commodity, or whether a specific cleaner scavenger is required. This is usually the case in most of your base metals scenarios, copper, zinc, lead, and can be the circuits where it probably requires more upgrading ratio through cleaning circuits, and or those extremely high recoveries combined with high upgrade ratios. So when it comes to test work for full Jameson circuits, Jon may have touched on this earlier, but essentially we can look at using our 3-stage dilution cleaner tests to establish a guidelines for the results and the performance we may see. And what we can do here is basically build a rougher 3-stage dilution cleaner test initially, and then from that build a cleaner stage 3-stage dilution test. And what this can indicate is the 2 target points of the 2 different circuits. Within the rougher circuit, we tend to find that obviously it's being a very high recovery, or the main target through the roughers tends to be the high recovery, is it ends up being sort of a very aggressive point that can be close to in line with a single stage of dilution cleaning test, basically. And then, as I said, we can build from that point to do the 3-stage dilution cleaner test to see where we would target through the cleaners. With more complex circuits, particularly things like sequential flotation circuits, where doing these sort of tests can become more difficult, having to produce or do basically a lot of flotation to generate samples for the testing. We can also actually look at sizing of conventional full mechanical cell circuits. So again, we then just basing it on the 3 stages of upgrading for certain stages, and then we'll match that performance. Or we have looked at lock cycle tests previously as well, which can become an easier option for understanding the possible full circuit results we can achieve. And then obviously Jameson Cell test rigs are available if there's enough sample. And then these are probably the best way, if possible, to generate results. And then we can use the pilot rigs to obviously run certain stages of the circuit, and then generate further samples downstream much easier using this process. So having a bit more of a look at some examples of what we would be looking at in terms of those flotation test results, and how we would build those into sizings of the circuits or targets. So this is here an example of a rougher scavenger 3-stage dilution cleaning test. So the bottom curve there, the purple one, was just single stage conventional cell, whereas the blue and green are showing 2 examples of what we may see with the Jameson Cell in comparison, the 3-stage dilution cleaner test. So we tend to have a basis of design. In this case, it was 75% recovery at 7% grade. And the first thing we would look at is, can we produce a final concentrate? And that would determine whether we would include that rougher scalper. And something important here is whether the recovery that we can achieve for that grade is enough to warrant having that cell. So in this scenario, it can maybe achieve 15% at the target final concentrate grade of 50%, which would be a discussion with the client, but may not be enough to warrant having a scalper in this scenario. Then we also have a look at what our final results can be, or our overall results can be, and can we then either target a higher concentrate grade for the same recovery, so possibly 10% in this case for the 75% recovery, or then can we push to a higher recovery fraction and achieve the same grade of around the 80%. Or we might find that the results are very similar, or there's only a very minor upgrade, which could be the case, which is like that middle curve, the blue curve there. So looking at then the fundamentals of that circuit and how sort of that may be designed, and the end result would be potentially in reality. So based on the this particular rougher 3-stage dilution cleaner test performance curve, which we see down the bottom, in this scenario, we would look to add a scalper, because a final concentrate grade can be achieved at quite a high recovery, possibly up to even sort of the 60-70% range. And we would install a scalper at the head of the circuit. Typically then this cell would be run more like a cleaner, with your deeper froth levels, higher wash waters, and potentially lower air, depending on what the carrying capacity requirements are, to achieve that final concentrate grade. May then also include a rougher cell after that scalper. This would maybe target that middlings sort of section, and we would alter the operating variables here to start to become more recovery focused. So it might run with medium frothlet depths and maybe some mild wash water and medium sort of airs. And if then the third scavenger cell was required, this would be obviously targeting that last portion of probably your composite materials, more difficult to float. And in conjunction, the cell would be typically run quite aggressive with shallow froth depths. You probably wouldn't have any wash water or very minimal. And depending on the carrying capacity requirements, you may look at things like froth crowders or lip extensions to make sure that the mass generated there is able to flow across to the launders. And so obviously those back two cells we're clearly in a zone which requires further liberation. And therefore, as I said, the key target here becomes recovery. So in terms of a cleaner, again, this could be a typical example of what we might see from the lab results. Again, the purple line there showing a single mechanical stage of cleaning. The green and blue lines are showing potential Jameson Cell results. And so for this example, they might have had a target of 75% recovery at 50% grade. So the key things we then have a look at, again, we're looking at cleaner scalpers first and possibly what sort of recoveries they're going to achieve. In this case, you may be looking at sort of the 50 or 70% mark, which is what you would be hoping to probably achieve in a scalper if you're utilising probably our conventional Jameson Cell cleaner flow sheet. This is obviously targeting that clearly liberated, easy floating material and should produce the bulk of the final concentrate. We then obviously have a look to see if we can potentially improve overall numbers again. Same sort of scenario where can we produce maybe a better concentrate or more recovery at the target concentrate grade. And once again, the three-stage dilution cleaner test may just confirm that it achieves what the design targets were based on maybe conventional mechanical cell tests. So here looking at, again, some results and how that would sort of translate into the circuit design. As mentioned, again, we look at the target zone for the scalper at the head of the circuit. Again, in terms of operation, you may be looking at some deeper froth depths and higher wash waters at this point. Air to pulp would be set up to match what probably the design mass pull is. So particularly if it's very high recovery stage, you might actually require a reasonable amount of air and quite a high air to pulp. Could be a bit lower if it's more in, say, the 40 to 50% zone. And then we generally have a closed scavenger and recleaner circuit. So the tail from the scalper would typically move to a cleaner scavenger, and then we would look to upgrade that remaining material to a recleaner and float off the rest of the available material at a target concentrate grade. So typically through here, again, obviously the scavenger we would operate just more aggressively because that has become the recovery unit. And the recleaner, it would likely have probably lower air rates than possibly your scalper due to, as I said, usually it requiring less mass production. It would also have the deep froth levels and a high wash water. And then essentially you would be looking to put it all together. And this probably highlights what would be our baseline full circuit for a Jameson concentrator. That would be based on base metals probably, tend to possibly be a little bit different for some other commodities, but this would be very much a starting point. And then we would only alter for things that would be specific to the specific scenario we're looking at. Just finally, this was a gold example, and is in a way quite a simple sort of full circuit one to have a look at, where it was based off some test work that was completed. So we got some Jameson Cell test work completed in the lab, compared that to the mechanical cells. What we found, obviously this site was specifically looking at 2 different composites that would be feed, that would have different results. So obviously we found that there was significantly improved upgrading ability in the Jameson cell compared to mechanical cells. We found that scalpers could achieve up to 80% in both scenarios at what the target final concentrate gold grade was, which was 22 grams per tonne, which the mechanical cells couldn't achieve actually throughout the test, through both the rougher ore cleaning stages. And in this scenario, we want to make sure we're using the highest mass pull scenario for design. So in this case, we'll be looking at the composite 2, which we're able to achieve the 92.2% recovery at the 22 grams per tonne of gold. Again, going back to that same principle that we want to design a circuit for the maximum scenario. So that in circuit scenarios includes the results as well. If they're going to see different feed, we want to make sure that if there's a high mass pull scenario, that we design for that. So what we ended up finding when it came to the circuit design was that it required simple 2-stage rougher scavenger circuit. As from the results that we found in the lab, we were able to pull very high recovery in a scalper cell. Anywhere, as I said, up towards that 80% mark was achievable at the final concentrate grade. So because of the low mass remaining, we only needed a single scavenger unit to recover that remaining material. And it was also being gold, very low mass pull scenario. So carrying capacity was not an issue at all with the 2 cells. It was a very high throughput scenario though. So we were looking at 8,512 cells here, our biggest cells in the rougher scavenger duty. And because of the extremely high throughput, we're looking at nearly 4,300 tonnes per hour of feed, and which equated to 13,680 metres cubed per hour of flotation feed that we needed for trains of rougher scavenger cells. So the rougher scavengers would recover obviously that remaining gold and send it to a cleaning circuit. Because again of the high volume, we were pushing to very high recovery points in the rougher circuit. The cleaners would still receive quite a high feed volume. And then we needed 2 of our B6500 cells in parallel to treat this. But this also worked out well with the 4 rougher scavenger trains, which would have 2 trains would have a single cleaning stage treating the concentrate from that scavenger. This would obviously produce the remaining final concentrate. But we also designed the circuit to make sure that the client had the option to send cleaner tails back to scavenger feed if it was found to be advantageous or required. During the test work, we found that it shouldn't be probably required, but as I said, if they felt they needed to put it back to the rougher scavenger in a closed loop, that could be done as well. And then essentially this was the final result in a 3D model of the circuit.
Fantastic. Thank you for joining us on the case study for going through the Jameson Cell to rougher. I feel this is a very, very valuable case study to discuss with you, particularly because it kind of demonstrates a lot of the success we've been seeing of late and a lot of the rougher applications that have really taken off of late. Now, the Jameson Cell, as Adam touched on earlier in this presentation, can find that we can recover particles from about 3 microns to about 300 relatively easy. When we did a case study on the Mount Isa installation, where we put 3B18 downcomer cells in, we found that we could get recoveries from about 93 to 97% chalcopyrite recovery from 3 to 300 microns. So the ability to float relatively coarse material is not new. But the question is, why are we going and being pushing into rougher cells of late? And this has fundamentally come down to volumetric capacity. We have been producing larger and larger cells. As you can see here, a lot of the new cells in those roughing duties of late have been really taken off since around 2019. Since then, we've developed the B8512, which allowed us to run an individual cell around 1500 tons per hour, all the way through to this new B10.516 that can run around 2000 tons per hour in a single cell. Being able to do this in a single cell makes everything much more cost effective and is one of the reasons why it really has taken off of late. Now, that Z8512 or BZ8512 model is this one image you have in the middle. And these cells were originally done to be developed on the ground. However, some applications put them in the air. At the time, it doubled the capacity of our largest cell, so the B6524. Those that don't know our naming convention, the number in front, so like B65 is the length of the cell, so 6.5 meters. Then the 24 is the number of downcomers. This cell itself can treat up to 1500 tons per hour, and we proved it at Cadia, where we commissioned one of these cells back in August 2022. Since then, we commissioned we've had B7B8512 units committed to the Ozorno project and have basic fundamental designs on the B10-1500. So the cells are getting bigger and hence the higher throughput they can handle. When you look at footprint constraints, that allows you to significantly reduce your footprint for those particular duties. Now, this cell, especially the cell Acadia, it was particularly a special cell. It was installed on the basis of previously done pilot work where an L500 was sent to site. What we did was we surveyed the existing bank. So in the graphs on the left, the black grade recovery curves are the existing surveys for copper and gold. And then we ran the pilot and saw what we could actually obtain with the same feed. Now, we knew the target total final con target was roughly 27% copper. And what we found here was you could actually achieve that for up to 60% of those copper units. So you could actually put a cell in as a scalper, remove 60% of the copper, then treat the rest of that material through another process. And this is fundamentally the methodology behind why the cell went in. The cell itself was getting copper upgrades up to about 90 times and gold upgrades to 70 times. And this whole scalping side of it allows you to significantly debottleneck and allow you to significantly reduce your footprint. Another one closer to home is a Jameson rougher scalper that we put in North America. This is a North American gold operation, and the really interesting things here was we expected some performance variation due to 5 different bands of ore that was expected. But in all applications, the average results have been around 91% copper gold recovery at 47 grams per ton grade. Now, that's from direct flotation feed. Their target point was around there. So as you can imagine, you turn the single cell on and you've recovered 90% of your gold recovery in this one Jameson cell at grade. So that's really, really exciting. It matched the full scale performance to the 3-stage dilution cleaning test. We didn't do any pilot work. So that's on the basis on how they proceeded. And lastly, the part that's most exciting is if you look at the density, it is far more than what you'd expect for a traditional rougher cell. At times, feed density was reaching 45 to 50% solids, even though as a rough rule of thumb that we design around 35% or less for rougher duties. So what I want to stress is if you ever want to operate high at that point, we always recommend some form of piloting on site, but this cell here demonstrates that the cell is versatile and flexible enough to go into those duties. In Central Asia, we put in a Jameson cell quite a few years ago at ZIF2 in gold processing. And what we found was 1B6524 in a rougher scalper capacity could achieve concentrate grades at around 70 grams per ton at 60% recovery, whilst feeding 1 gram per ton of gold at the time. And the results from site are on the right there. And what we found was there was a high degree of confidence from site in the performance of the Jameson Cell technology. This was demonstrated via the site purchasing another 9 units over 3 years. And this was multiple cells as rough scalpers and cleaning duties. So that real scalping shearing effect that works in the downcomer really, really worked well here. And I wanted to put a pilot in just because it's a good example to explain operations. There is a common misconception in industry that the Jameson cell was never designed on the basis of achieving recovery. This is completely false. Jameson cell will operate in the way you want it to operate. So to demonstrate this, we ran an L500 rig over several different days to test all sections of the grade recovery curve to show and demonstrate that the cell itself can operate down there. What we found in this case was the cell itself could exceed the target grade of 27% copper at about 80% unit recovery when run optimally. And if it had the same grade target as the previous site, that could be a prime opportunity for a rough scalper. But either way, the purpose of this was to show that recovery is not a limiting step on the application in rougher duties. Now, I'd like to talk to you about the Mount Isa concentrator. The Mount Isa concentrator is actually a really, really good example to show you the benefits of the footprint savings that you can expect with a Jameson cell. The cells itself, where we put in 3 B18 downcomer cells in a charcoal pyrite cleaning duty. And the idea here was to upgrade the existing cleaners and replace a lot of the old equipment around the plant. These 3 Jameson cells replace 3 2.5 meter columns, 2 recleaner banks of about 68 cubes, 3 cleaning banks of 102 cubes, and 2 retreat banks of 68 meters cubed, which is a lot of volume, as you can see. The cells themselves, as you can see, we've replaced what we've highlighted in red with what we have in green. These are based on a scalper, cleaner, and a cleaner scalper, all producing the final concentrate. In this example, we found that there was a 76% reduction in flotation surface area by replacing these cells with 3 Jameson cells. We found a 62% reduction in flotation volume and a 70% reduction in residence time. Those are big numbers, but I always feel it's best to demonstrate this visually. And if you look on the right here, everything in red was replaced with what's been put in green. And that's what I really want to stress when I talk about footprint savings. The cells can do everything in a much smaller area and do as well, if not better, than your existing solution. Once we were done, we found that we wanted to survey the cell and demonstrate benefits. So JKMRC came in and conducted a survey of the cells. While we know that the small bubbles that were generated by the Jameson cells are good for fines recovery, as you can see with copper recovery here, from the plus 38 to minus C5 fraction, it's also good at the coarse. And in this example was the one where we found charcoal pyrite could be recovered from 3 to 300 microns between 93 and 97% recovery, which obviously show the benefits of the technology. The flotation circuit, we went back and looked at size by size recovery, and when we had a last survey done in May 2014, we found that this grade recovery curve in green was what the site was seeing. We then replaced all the equipment with these 3 Jameson cells, redid the survey in March 2016, and plotted the two curves together. What we found was we get the same concentrate grade, but we find a significant improvement in fines recovery. So in this case, we reduced the amount of equipment that needed to be operated, we significantly reduced the footprint, and we did better than the existing circuit, which is why this is one of our big success stories. Azorne. Azorne is a very good case study, and it's actually quite interesting. It's been brought up a lot, and I think it's a really good demonstration of what you can save in OPEX, CAPEX, and ESG, actually. Looking at a Jameson concentrator, which Azorne is basically the combination of multiple Jameson cells with isomills. By putting it all together, you can have significant savings in CAPEX, just basically due to footprint reductions and reduced equipment. Significant savings in OPEX because you're not paying for conventional agitators style designs. There are environmental savings where you get that smaller footprint, which is significant, and less noise due to less blowers, less agitators. And most importantly, you get significant performance improvement due to the Jameson cell technology with the isomill. Jameson cells will improve your fine particle recovery, allow for high upgrade ratios of concentrate, reduce the circuit volume, allowing you for much better response time and ability to handle variations. And I know this is a general term, but there is potential to reduce cells between 50 to 75%. As a rough rule of thumb, we found 1 Jameson cell typically replaces 4 conventional cells. Less cells, more simple operation. The Azorne project is actually a complex lead zinc iron ore body. It has a multi-stage rougher scavenger system and driven by a very strong chemistry-driven cleaning approach. What we did in this case was we reduced the footprint of the plant by about 70% compared to the conventional operation. The footprint I've got here on the right, the white grid marking is what was done originally for Azorne, and the colored model is what we designed and put in for them. And that cell was able to achieve what the entire footprint of the larger one was meant to do. So we've already addressed that it's smaller in footprint, but what about building height? Since this is in a cold climate, a building had to be built around the plant. And what we found was we were able to reduce the height of the building by about 15 meters when compared to conventional flotation cells. Some of the key aspects here are, since you don't actually have to lift out your agitator, you can significantly reduce the height of the building as you only need about 2 meters clearance above the Jameson cell in the rare case that you'd have to replace a downcomer. This was the final cell design. If those that are interested, we actually have a good fly through on our YouTube page, and which will show you the footprint and fly through and demonstrate how it all looks from a operator's perspective. When we did the OPEX comparison, we found, compared to the conventional circuit design and the Jameson cell design, we found we're able to save about 6 million per annum just on power. And going through everything else, reduce total OPEX by about 12 million a year. And I've got summaries of both those plants put here, looking at the conventional cell design versus the Jameson concentrator. So there is the ability to save significantly on power in these designs. Now, taking power, and power is a major one, particularly on ESG analysis, We went back and recalculated the amount of coal that would need to be consumed to actually maintain both of these plants. And what we found was you needed about 30% reduction in coal consumption for this Jameson concentrator design versus conventional. And that resulted in the 30% reduction in coal. So while less power, you get less power savings and you get better ESG credentials when you reduce your emissions as well. So all in all, it's a smaller, more efficient design with a lower footprint. New Britannia. New Britannia is a Jameson concentrator up in North America, a lot closer to home. And the Jameson this is the second Jameson concentrator that was being commissioned and is a very, very good success. The New Britannia flow sheet is up here in front of you. It is a rod mill ball mill circuit targeting a grind size of about 75 microns. They have two Woodgrove DFR cells up as a pre-float that were done as a talc pre-flotation mechanism. And the tails from there fed the Jameson concentrator, where we had three E17324 cells in rougher scavenging duties and one Z1200 as a cleaner. Something I really would like to stress is this cell, this circuit, while significantly smaller, had extreme operating flexibility. Rougher 1 concentrate has the ability to report to final con or a cleaner. Rougher 2 can report to rougher 1 or the cleaner. Cleaner tails can report to rougher 1 or rougher 2. So depending on the ore body at the time, they have flexibility to deal with it in the small circuit. And this is the entire circuit here in one photo. Probably the smallest flotation circuit I've seen in general, but it's a very efficient design and very compact. Now, the circuit is currently operating at full capacity. When this was originally went to go in, 4 Jameson cells replaced 12 tank cells. By doing so, they reduced their need to install blowers or compressors. They found in their trade-off study with Hudbay that they had 50% less footprint and power. And probably the most exciting part was they water commissioned the entire float circuit within 2 days. They achieved their tails grade feeding the gold CIP circuit within 24 hours. The way the circuit is designed to operate is they want to try and remove as much copper before they feed the CIP circuit. And as I addressed earlier on in this presentation, one of the common industry misconceptions is that the Jameson cell can't achieve recovery. Here they commissioned a full flotation circuit and achieved target within 24 hours. So it's going really, really well. The plant performance currently is exceeding expectations. They have exceeded their upgrade ratios at these high recoveries compared to the L500 test work. And another point I actually do want to stress is when they went ahead, they actually did L500 test work on the ore body to get an understanding of what was going to go in. The L500 is so simple that they actually got accounting students to do the test work. It's that simple and that easy to operate. The rest of it really shows the flexibility and ease of the cell. So why did they go with Jameson cells? And one of the key aspects was due to variability. New Britannia has 2 distinct ore zones, one low copper, high talc ore body, one low talc, high copper. Grade can vary anywhere between 0.2 to 3.5%. And so they had to design a cell that was able to handle that variability. Now, I know the first thing that's probably come to your mind is why didn't they just do a mine plan to try and blend this out? And quite simply is they are mine constrained and therefore it's pretty much hand-to-mouth feed. So the cells themselves have to basically be able to handle this variability. If you understand your carrying capacity constraints and volumetric flows, it's easy enough to manage that risk into your circuits. And that's what they did and produced a very robust, flexible circuit design that was able to handle that high variability, which led to significant metallurgical performance. And this is the entire copper float circuit page. And there are a few things that I do want to mention. apart from the simplicity of a whole float circuit on one page, is on the bottom left, you can actually see the process stability. That internal recycle mechanism keeps everything steady, and in that keeps performance operating a lot better. Another area is the ability to actually instrument cells on the run. The Jameson Cell allows you to monitor your vacuum, your air rate, downcomer flow, wash water, froth depths, recycle, and allows you to calculate your jet velocity. What this means is you can actually have indications if something is up with the cell prior to any maintenance inspections. This allows you to get a better idea of how your equipment is running on the run versus me shutting down a cell and then doing a yearly inspection to find out, example, half a stator is missing. This gives you a lot more control on how you want to operate the cells and give much more reasonable set point targets to operators on how to run the cell. So it does really help the general operation of this circuit. Since commissioning, flotation feed is varied between 1.1% copper through to 2.7% copper. And interestingly, there have been a few reasons in how it's been performing and challenges. The circuit started slurry in about November 2022. They didn't actually have an OSA commissioned until February 2022. And this is predominantly through the design of the OSA system, not having valving for flushing, bad out design on 90-degree elbows. And this obviously makes commissioning a challenge when you have to wait a day for results. They also found that there was an issue with the reagent system. Effectively, the DFRs were taken offline for a period of time. Circuit was not getting the talc rejection as it was designed to do, and therefore additional CMC dosing was required. Since you're adding so much more than you originally expected, we found that the dosing pumps had an ability to hold prime, and there was no feedback to the control room, and that they were undersized for the duty for that much reagent that they were adding. These obviously have impacts on grades and can cause some deviation, but it explains some of the performance of late. As you can see, they were targeting about 0.1% copper in tails target, and they've pretty much operated that since. The site itself has the luxury of blending its concentrate with Stall, which is about 5 kilometers down the road. Therefore, their operating target, while variable, is normally between 15 to 20% copper. Recovery of copper has sat pretty much on target as well, around that 90% copper. The cell itself has probably one of the quickest ramp-up commissionings I've personally seen. It sits on curve 1A for tonnage and copper production and gold and copper production, showing you the flexibility and ease of getting these cells back online at a very accelerated manner. And I'd like to thank you for sitting through this CMC short course presentation. If there's any questions at any time, please feel free to reach out to myself or the team back in Brisbane. Thank you.